Yes, hello everyone, and welcome to the Frontiers of Parameterized Complexity. Our speaker today is Eduard Eiben, who will speak on removing connecting obstacles in the plane is FPT. Please, Eduard, go ahead.
Yeah, thank you for the introduction and thank you for invitation. So, as Fedor said, I'm going to speak about removing connected obstacles in the plane, and this is joint work with Daniel Lokshtanov. So let's start. Yeah. So basically, let's start with a problem definition the definition of a problem that we are studying. So basically, what we have kind of a set of obstacles in the plane. These obstacles are basically kind of a closed, connected subsets of a plane. And so, for example, we can have this big obstacle here. And these obstacles also are allowed to have some holes in them. And what we want basically, so we have these obstacles and we have 2 points, S and T. And our question is, so basically we want to get from S to T, and it's not always possible, right? And in this case, there is no way to get from S to T without crossing some obstacles. So our goal is to get from S to T with crossing as little obstacle as possible. So more formally, we are given also some bound K, and we are asked whether we can get from S to T by crossing at most K obstacles. We can cross the same obstacle multiple times, and it still counts as just one obstacle, which means that this question is kind of equivalent to asking, can we remove at most K obstacles such that there is a obstacle-free path from S to T. And in this case, we can see that we need to remove at least 2 obstacles, and 2 obstacles is indeed sufficient. If we remove this obstacle, this green obstacle here, and this purple obstacle here, then we can get a path like this that only intersect the green obstacle and this purple one, even though it intersects green one several times. I hope the setting is clear. Now a little bit of a motivation of this problem. This problem is kind of motivated from 2 different areas and was studied in 2 different areas. So first, motivation is kind of connected to motion planning. And in motion planning, basically goal is we are having some robot, and we want to move this robot from a starting position to the end position. And there are some obstacles, and we don't want this robot to collide with these obstacles, or we want it to collide only with few of these obstacles. So this kind of problem is usually referred to as a piano mover, because it's about moving a piano between 2 places. And our problem is a little bit different, and it could be kind of considered as a simplified version of this problem. There are kind of 2 simplifications. First, our problem is only in the plane, and second, our robot is only a point robot. And in this setting, in the motion planning setting, this problem was studied under name minimum constraint removal. In sensor networks, we basically have sensors that cover some region. These sensors are usually unit disks, but not necessarily. It could be general disk if we have sensors of different strengths, but it could be a sensor also of different shapes. And here, basically, the idea is that these sensors are guarding something. So, for example, you are guarding a gallery and some especially expensive painting in the gallery, and your question is how many of these sensors would need to break such that you can get from between these between some given 2 points undetected. So in the gallery case and the expensive painting case would be from the entrance to the painting, basically. And in this setting, it was basically studied under name barrier coverage or barrier resilience. And just to note, determining whether there exists an obstacle-free or barrier-free path is polynomially solvable, meaning that we also kind of need to assume that we are given somehow these obstacles, and these obstacles are not as complicated, so they cannot be given on an input. But in general, once we have this, actually this problem can be solved in polynomial time, just to decide whether there is a path. For us to study this problem, and especially to give our FPT algorithm, it was actually much more convenient to look at this problem as a graph problem. And we can obtain a graph problem from our problem as follows. So basically, we can look at the regions, or basically faces we get in the graph, and we look how in the plane, when we look how the plane is subdivided by the borders of our obstacles, and we put a vertex in every region. In every region of this introduced by these borders, and we put an edge between two regions or two faces if they share a border of some obstacle. Right. So, for example, we put vertex here in this region, which this region is identified by intersection of this purple and orange obstacle. Right? So we have this region here, and we put vertex here. We put another vertex here that is identified by this purple obstacle minus this orange one, and we put an edge between them because they share a part of the border of the orange obstacle. Now we associate every obstacle in the plane with a color, and every vertex also gets a set of colors, and the set of colors the vertex gets is exactly the set of obstacles that intersect in that region where we place the vertex. So, for example, this vertex would get an orange color and the purple color. This vertex would just get purple. Here it would be, I think that's cyan and pink. And there of course, we have also some vertices that don't get any color, for example, as here, or this vertex here, or our final vertex T. And we just call such vertices empty vertices. Now, in this generalization, what we are looking for is we are looking for a path in a graph, and we say that a path is k-valid if it uses at most k color, meaning that the union of the colors on all vertices of the path is at most k. So the number of the colors in the union of all colors on the vertices. Now, as a graph problem, this can be formulated as what we call obstacle removal problem. And here we have a vertex colored planar graph. So note that the graph that we obtain is planar. You can also study a problem where you don't have a planar graph. But in our case, we only kind of consider the planar one. And you are given two vertices S and T and an integer k. And the vertices are colored, and every vertex does not necessarily have only one color, but has a set of colors. And the question is if there is a k-valid path between the starting and final vertex. And the other thing that we need to notice about all the instances that we got from our original problem, and that is not yet covered by this definition of the obstacle removal, is that we were starting with an obstacles that are kind of connected subsets of a plane, which means that using this reduction to this graph problem, we had additional property, and that is property that we call color connectivity, which is that for every color in the graph, the set of vertices on which this color appears induces a connected subgraph. And we call, how large can be auxiliary graph? So it depends on the number of different intersection and different regions, and so I think we were always assuming that it's polynomial, and right now I don't remember if we had reason why, but I think it because it would anyhow increase the complexity of the problem if we had too many intersection and too many kind of very wild regions. Right, so because the number of vertices of the graph is exactly kind of a number of different regions that we have in the plane introduced by these obstacles. So it probably could be exponential in number of obstacles or number of colors, but probably not much larger than encoding of the instance. But right now I don't exactly remember whether we had a good argument why is it small in the instance, but I think we did. I just don't remember it right now. Okay, so what was I saying? I was saying that we have now this graph problem, and we are studying this graph problem. And I was saying that there is this important property that is a color connectivity property. And actually, the algorithm that we get for the problem, we get the algorithm for this connected obstacle removal, such that every color is connected. And this is basically the only problem we studied in this paper, but of course the more general problem was also studied before. Before I go to the algorithm, let me say a little bit about the related work. So the first to study this problem, at least as far as I know, was Kumar, Lai, and Arora, and they studied it in the motivation from wireless computing. And basically, they show that if you look at just unit disk obstacle and also just some kind of a restricted configuration of these unit disks, then you are able to solve it in polynomial time. However, they were not able to resolve the general regions or general configuration of unit disk obstacles. And actually, as far as I know, it is still open whether for just unit disk obstacles the problem is polynomially solvable or NP-hard. Later, Berger Kirkpatrick showed that actually, if you have for unit disks, if you have a path, if there exists a path that intersects at most k unit disks, then it never needs to intersect a same unit disk more than 3 times. So basically, the length of this path would be at most 3 times number of colors that or number of obstacles that we have on this path. And using this bound on the length, Corman et al. Gave FPT algorithm for unit disks and extended it also to some little bit more general regions that basically to kind of regions that are close to unit disk but are allowed to be a little bit more wound. From the negative side, I'll show that the problem is NP hard even when the obstacles are just line segments, and even when no free line segments intersect at the same point. And at the basically same time, Thank and Kirkpatrick showed that it is NP hard also when there are just unit length obstacles. And there are also a lot of other NP hardness results showing that this problem is NP hard already when obstacles are very simple. So even when we have like axis parallel rectangles, or even if we have same size squares but we allowed to rotate them. So not necessarily, so not axis parallel squares, but squares. Then we with Kant and Yugdal, we gave some exact heuristic algorithms, and with IAD we also gave algorithm by k plus 3 width or k plus length of the optimal path, which basically, if you look k plus length of the optimal path, basically generalizes the algorithm by Corman by kind of a lot, because their idea for unit disks was first show that for unit disk you get bounded length of the optimal path, and then that you get bounded length, and then you use both, that you have unit disk and bounded length to actually obtain the FPT. And we show that the bounded length is enough, and we don't need unit disks or any structure of the obstacle. Since the problem is NP hard, there was also some approximation study or some approximation results on the problem. First, where Berg and Kirkpatrick in the same paper that they showed that for the unit disks, the length of the optimal path is at most 3 times the number of colors. They gave 3 approximation for unit disks, and even 2 approximation if S and T are well separated. Whatever is not important what that means right now. It's just that there is a little bit better approximation for well separated, and later it was even improved to 1.5 approximation. From a little bit negative point, it was shown that the problem is APX hard, and even for rectilinear polygons, general disks, and also for the graph problem. Oh, it's APX hard, but also the same authors also gave O square root of n approximation. And finally, very recently, I think it's this year's Soda paper, Kumar et al. Gave constant factor approximation for arbitrary obstacles. Also, actually, they gave constant factor approximation for the graph problem, for the connected obstacle removal. So the graph problem where all obstacles are connected. There was also study on the more general problem where we don't necessarily need the connectedness of the colors. And this, I believe, Hauser was the first one to study and showed that it is NP hard via reduction from set cover, which even though not mentioned, is actually FPT reduction implying W2 hardness of this for this problem, parameterized by K. note that this is the not connected obstacle version of the problem, so it does not contradict our FPT result. Right? They also gave some heuristic algorithms, and later Gorbenko and Popov gave some other heuristic algorithms by reduction to SAT. And finally, or actually not finally, but then we with IAT, we extended this W2 hardness to W SAT hardness, even for f of k approximation. And again, in the same Soda paper, Kumar et al. Gave even much stronger lower bounds for approximation, assuming dense versus random conjecture. Okay, and now finally, I get to our result, and basically for the rest of the talk, I will sketch you the proof of this result, that for the connected obstacle removal is FPT parameterized by K. So the number of colors or number of obstacles that need to be removed to get an obstacle-free path. Okay, and yeah, so we are looking at the graph problem, and let us start the sketch of the proof by looking at kind of a structure of an optimal path. So how some path that uses at most k color can look. So we have this ST path, and we have vertices on this path, and each vertex has some color set on it, possibly empty color set. Okay. So the first thing that we can notice, that we can split our path in basically kind of depending on how many colors we have on the prefix up to given vertex, right? So here at this vertex we have just one color. From here starting, we have already 3 colors on the prefix of the path. Here we still have just 3 colors because we have just 1, 2, and 3. But here we finally have now 5 colors. We have 5 colors also on these next 2 vertices. Then we introduce the 6th color, color 6, which is enough up to this point. And then we finally introduce the 7th color, and with this color we reach the final vertex. And now this kind of introduces us some k+1 important vertices, including S and T. And basically, these important vertices are for each I, the last vertex that can be reached by at most I colors, right? So this is the last vertex that can be reached by 1 color, but also the last vertex that can be reached by 2 colors. This is the last vertex that can be reached by 3 colors, but also the last vertex that can be reached by 4 colors, because here we already need 5 colors to reach this vertex on this path only, right? So it's possible that there might be a shorter path, but on this path using less colors, but on this path we need 5 colors to reach this. Here we have last vertex that for which we need 5 colors, and so on. Okay, and now our algorithm would kind of runs in k rounds, and in each round we are trying to identify possible vertices and possible paths that we can reach these vertices, such that these vertex can be possible ith important vertex, right? So for example, in fifth round, we want to kind of identify, we want to have this vertex. I want to say, okay, to have this vertex as the last vertex reached by 5 colors, we want to find kind of all possible, or we want to consider all possible paths to reach this vertex. And we don't necessarily want to keep all such paths, but we want to at least compute some sets of these paths that we can use to reach V in our in some optimal path, right? So for example, even though our optimal path was this black one, maybe we do not have we do not keep this black path in our set, but we have, for example, this green one that can replace it. And basically, the other important observation is that we will be not actually keeping exact paths how we can get from S to V during our algorithm, but we will be kind of going to and from between paths and color set of a path. And we can do this because if we have a path, then we can easily get the color set of this path by just looking on every vertex and checking and just collecting all the colors that we have on the path. And on the other hand, if we have a color set that on which we can reach from S to V, then we can just take only the vertices that contains some subset of these colors. So we can keep only the vertices that does not contain any other color in this color set, and we can run our favorite reachability algorithm to get a path, like BFS, for example. Right, and now for a little bit, it will be more convenient for us to actually speak about color sets that we use to reach the vertex V instead of paths that we use to reach V from S. And now the thing is that if we have, so now our representative family is basically a set at ith step is for every vertex we have some family or some set of color sets. Each color set has exactly I colors, and each of these color sets can be used to reach V from S. Now, if we have such families for all j smaller than I, then it is relatively simple to find some representative family for I by just basically taking some vertex, looking at all the color sets in the representative family we have for this vertex, and trying to extend this representative family by some color of a neighbor of this vertex.
Sorry, there's a question also. Yeah. Yeah, from Bart.
Yeah. Yes. So here on this picture, it's kind of each different color represents a different color set used to reach V. Yeah, and the color sets they can intersect in some color, so they're not necessarily color disjoint color sets, but they should be different color sets. Yeah, and as I was saying, if we have some representative families for j smaller than I, so for previous steps, then to get some representative family, for the I step is relatively simple by trying just to extend the color sets we have in our families by the color set of some vertex. But the problem is that this can get very easily XP if we don't reduce the size of the color set in each step, right? So you can imagine on the picture up here, the path from S to T, or especially from S to V, it can be kind of like a path of diamonds like this, and you can imagine that that any combination how you go through these diamonds give you a different color set. So you can imagine that there are XP many color sets to reach from S to V. Right. So now the important thing, or important part of our proof, or even I would say most important part, is to figure out how to reduce the number of color sets at every point. And we will actually, what we will be doing, we will be fixing one vertex and some color sets that we have to reach this vertex. And we will try to only reduce the color sets that we need to reach this vertex V, assuming that this vertex V would be the last, it would be the important vertex that we introduced for, so ith important vertex if we are looking into step I. Right, so now we have fixed a vertex, we fixed some family of color sets. Each color set has I colors, and we also have fixed I. And now basically, I would say a main result of our paper is that if this family of color sets is larger than some k to the O of k cubed, then we can actually find one color set in this family such that even if we remove this color set, so if there is an optimal path that uses this color set to reach V, and V is important vertex on this path, then we can replace the starting part of the path that uses colors in P by a different path that uses colors in P prime to reach V, and we still have an ST path with at most k colors. Now, here there was also one technicality, that in the second part we don't assume that V is also the last vertex where we use at most I color in this new improved path that uses this P prime. So there was some technicalities to actually show that we can be removing always that we can do it kind of iteratively and always removing one color set by one color sets. But if we fixed some kind of extremal path, then we were able to do this. So let us just look how we actually show this lemma, that we can find this this color set that is kind of irrelevant. And basically, the main idea is that instead of trying to find this color set in the whole family of color sets, we actually try to find a smaller family, but it is still that is still very large, but that it's somehow structured. Like somehow structured will be clear a little bit later. And actually, here to get the structure, we will also go once again from the color sets to the paths. But yeah, but the main idea is to get some subset that is still large, but it's just a subset of the paths, and where we can find some kind of a structure that makes it much easier to identify a redundant color set. Okay, so the first step, or the first important tool that we needed to use to get the first kind of structural restriction. So the first thing that we needed to use was the sunflower lemma, that is basically a sunflower. If we have some sets of or some family of sets, so in this case family of color sets, and each color set has same size, or a size at most k, basically, or each of size exactly k, or in our case it would be each of size I, because we have color sets of size I and fixed I. And the sunflower is, we have some core, so some subset, such that the intersection of any two sets in our family, so in our sunflower, is precisely this C, right? So it looks something like on this picture. So there is some sets of color that is the same for all our color sets, and for otherwise all sets are pairwise disjoint outside of this core. And it is well known that if a family is large, so if we have at least this many sets of size k, then it contains sunflower with at least L sets, and moreover, this sunflower can also be found in polynomial time. Now, so the first thing we do, we apply a sunflower lemma on our family of color sets and find a large sunflower. Notice that because size of our color set at the beginning was at least k to the O of k cubed, and all of our color sets had exactly I colors, where I is more than k, then we can find a sunflower that has size at least k to O of k squared. And let's see with this colors in the core. So C is the set of colors that is in all of our color sets in Q1. Now, the first thing that we were able to show is basically, now when we are focusing on finding an irrelevant color set only inside the sunflower, then the core of the sunflower is not important, right? So you can kind of imagine that if we find, so for P, if we find a replacement after removing the colors in C completely from the graph and decreasing k by size of C, and if you find the replacement among only these paths in Q1 basically, then after putting back the colors in C, because they are put back to both P and the replacement path, and because k, so the size of the path, the number of colors that we are looking for, is also increased by by size of C, that it is not then too difficult to actually show formally that this is okay. So removing the colors that are in the core of sunflower is okay, and we do so. And now from after that, we have that all the color sets in Q1 will be pairwise color disjoint, because they only intersected in C, and we removed C from the instance. Now the second observation, or a second lemma that we need, is that now, especially after removing the colors, even if this was not the case before we removed these colors in C, after removing these colors, it can happen that we have two vertices that now have exactly the same color set, and they have edge between them. And now we kind of need later in our proof that we don't have that this situation does not happen. And basically, because we are only caring about color sets that can be used to reach from S to V, then it is not difficult to see that the two vertices that have exactly the same colors and color sets and edge between them, we can easily just contract. And if we find if V was reachable from S before contracting, that it's also reachable from S after contracting using the same color set. Okay, so from now on, we can assume that we have this set Q1 of color sets that there are pairwise color disjoint, and we can also assume that in our graph, two neighboring vertices have different color sets. This is important, especially when saying that if we have an empty vertex, so vertex that has empty set of colors, then all of the neighbors of this vertex will have some color. And especially, it's important to notice that all of these vertices will be that none of these vertices will be on two different paths, or can be on two different paths associated with two different color sets in Q1, because Q1 are color disjoint. Okay, so now we have this Q1 family of pairwise disjoint color sets, each of size I, and V is reachable from S by each color set in Q1. Now we actually needed to go back from the color sets to the paths, and for this, for each color set, we fix one SV path that uses exactly all the colors in Q. This was important for us that this path uses exactly all the colors in Q, and basically we could deal with the ones where for example BFS would find actually a path that only contains subset of colors in Q by basically saying that this color set we can remove from Q1 because it would be dealt with for some J smaller than I. So we could assume that we have this, that now we have situation something like this. So now we are back to the paths instead of color sets. But the sets of colors on these paths are pairwise disjoint. And we can also then notice that because all of these paths contain S and V necessarily are empty. And because they are empty and because we did this color contraction, all of the second vertices on every path, none of these vertices appear on 2 of the paths. And we can kind of order our paths now depending kind of on a rotation around this vertex S in the plane, right? So remember that the graph we have is a plane graph. Now, basically, we want to still find some subsets of this path, and the structure we are kind of aiming for looks something like this. So we have some small set of vertices here, just 2, U1 and U2, such that all paths in our set passes through U1 and through U2 in the same order, but they do not intersect anywhere else. And even though we actually didn't get exactly the same structure, we got something similar, and we got it actually in kind of 2 steps. So the first step is to actually find such structure that we have this small set, some set U of size at most 2k, such that all paths intersect all the vertices in U in exactly the same order. But then in the rest, instead of the paths being completely disjoint outside of this set U, they are allowed to intersect, but they're allowed, but at every vertex outside of U and S and V is allowed to be only on some small fraction of all paths. So more precisely, now we are able to find some subset of these paths Q2, where and some set U of size at most 2k, such that all the paths intersect all the vertices in U in the same order, but for every vertex outside of U and SV, at most some fraction that depends on size of U and K of paths can contain this vertex W. Actually, the algorithm to obtain this is rather simple. It's more difficult to actually argue the correctness of the algorithm. So basically, you start with your full set, and U being empty. You pick the vertex that appears on most of your paths. You check whether the number of paths this vertex appears on is larger or smaller than this structure, than this fraction that we kind of want. If it's larger, then we add this vertex W to U, restrict ourselves only to all the paths that contain this vertex U, and repeat until you don't find any vertex that contains more than this fraction. But actually, this fraction is actually much smaller than what we want to. So what we want to is here this U plus 1, and in this fraction that we have here, we have U plus 1 factorial. That is because in this last step here, we try all possible orderings of vertices in U and pick the one with the most number of color sets. And the only kind of like the most important question that is not completely clear, why is it true, is why this stops after at most 2k steps, right? So why U cannot be larger than 2k. And basically, the important thing is that because this our set of paths at the beginning was large, at the 2k plus first step, we still have at least 3 paths that intersect each vertices in U in exactly same order. And because these vertices, these UI vertices, there is 2k plus 1 of them, we can kind of show that we can kind of show that there has to be one path that would need to have at least k plus 1 colors, but that's impossible because all of these paths contains exactly I colors, which is smaller than k. I mean, there will be one path that contains k plus 1 colors. And basically the reason is that, for example, in this case here, W is kind of cut by this path and this path from the rest of the red path, so from the rest of this middle path, and that's why it cannot, the color of W cannot be repeated again. And then basically you can say or color here and so on, and somehow you're able to argue that you would need at least k plus 1 colors if the algorithm didn't stop after 2k steps. Okay, we are actually nearing to the end, which is very good because I don't have much time anymore. Okay, so once we have this, so we have every path now intersect all vertices in U in the same order, and every other vertex appears only on some small fraction of the paths. What we can now show, so we can now first notice that if we look at 2 different paths that are kind of far apart, and we look at any curve starting from, so we are now looking at 2 paths, and we are looking between some UI and UI plus 1, and we now order these paths not depending how we order them at the beginning, but we order them depending on the rotation after UI. And we look at the 2 paths that are kind of far apart, and we look at some curve starting from this vertex, starting from, for example, W2 going to W6, and looking at that intersects only at the vertices of the paths. That intersects the paths only at the vertices. And we notice that in the plane graph, this is a separator, right? That separates vertices W3, W4, W5 from UI plus 1, which means that this gives us somehow lower bound on the number of vertices on this curve, because if we have only very few vertices on this curve, then there would be vertex that intersects more than constant fraction, more than these fraction that we wanted of a paths, right? Because all these paths in here, they have all these paths from UI to UI plus 1 have to pass through this separator. And the other thing is that if 2 paths intersect, then we can actually find a curve that intersect at most 2k vertices of a path. And it's kind of because we can use shortcuts between the 2 vertices that contain the same color. right? So for example, if this vertex and this vertex would contain the same color, then we know that there is a path between them such that every vertex on this path contains this color. But we also know that if you look on this kind of a boundary here, we cannot have this color. Like if you look on the boundary in just given by this is probably not the good one. I wanted boundary just given by a path that I'm not looking at, so not the blue one, but about a different path. Then this blue path, so this path of the color that is on both of these vertices, cannot intersect any other path because all the other paths contain only different colors than this path. Right? So basically, because we have only k colors on the path, there is a kind of a curve that intersects all at most k vertices that gets to the intersection, and the same curve and the same reasoning, we have curved and intersect at most k vertices to get back to the other vertex v5, meaning that combination of these two kind of lemmas tells us that if two vertices are very far apart, so two starting points of a path from ui to ui plus 1 are far apart, then these two paths cannot intersect, which means that we get structure like this, kind of, if we applied it for every pair of consecutive ui. So and also for S and U1 and the last UI and V. And the last observation is that, for example, if we have T here, so T is kind of course, it does not necessarily need to be exactly like this. T can be inside some of these kind of onions, and they also these onions can actually little bit intersect, but the idea is that if it looks roughly like this, so we have these kind of onions, T is outside, then this red path cannot share a color with any path that we use to finish our optimal path, to finish the path from V to T. So if our optimal path is from S using this red path to V and from V to T, then we can show that any color, so if the W shares that the W cannot share a color with the path, with this blue path, because this blue path would need to pass through many layers of this onion, and we can show that in every layer it has to have a new different color, or not necessarily in every layer, but in every second layer it needs to have a new fresh color. And if the number of layers is more than 2k or more than some O of k, then we would need to have more than k colors to actually reach this region to share a color. So only to share the color, we have to have, the path have to have actually vertex somewhere here, which would mean that we have too many colors on the path from V to T, which means that if this path from S to V and from V to T does not share any color, then because in our family all color sets were of size I, so exactly the same number of colors, we can replace this red path by any other path in our set. So we can remove this red path and the color set of this red path from our family of color sets, and that's basically finishes the proof. Right. So this gives FPT algorithm parameterized by just K, which we left unresolved in our iCalc paper with IAT. And there are still some interesting open question for the problem, especially, for example, polynomial time algorithm for the case of unit disks, but also, for example, if we have instances where no obstacles intersect more than constant number of other obstacles, right? So if the different if at every point intersect only constant number of obstacles, that is NP hard already for obstacle being line segments. But if an obstacle can intersect only constant number of other ones, it's still not clear whether this can be solved in polynomial time or not. And finally, it might be also interesting whether to figure out whether this k to the k cubed is optimal or there is a better algorithm. Okay. So that's it. Thank you for your attention.
Thank you very much.
You have questions. Yeah.
Thank you very much. Questions, please.
Yeah. Peter? I see. Or at least I saw a hand up. Oh, it wasn't a hand up. It was a clap.
I don't know.
Yeah.
So what happens if instead of unit disk obstacles, you consider the problem in 3D with unit balls? Did anyone study this problem, or has become much more complicated?
So I know that going to 3D it becomes much more complicated, but I'm not sure about the unit balls. So I'm not sure whether it's already known for unit balls to be NP complete, but like in general, going to 3D, if you're not doing unit balls, but you're doing kind of any obstacles, then you can kind of model the more general problem where the obstacles are not connected, and that problem is much harder than.
So from practical consideration, to me it looks more reasonable would be even to add the weights, right? Because not just you hit one obstacle, you have to go through it, and
yeah,
it's easier to go through one obstacle than through the other.
Yes.
Or it's easier to remove. But so what happens even if you add constant weights to the obstacles?
It's a good question. I think if they are just constant, like you have a integer constant weight, then it might be still.
So you want to remove
still possible,
obstacles, but of minimum weight now.
Yeah, it's a good question. It probably becomes a bit harder. Or it definitely becomes harder, but how much? I didn't think about it.
Okay, yeah. So, any other questions? Yeah, no, then thank you once again for a nice. Oh, sorry.
Oh, yeah.
Sorry.
Piotr, yes.
For constant weights, I assume you just can add copies of obstacles. But
yeah. So I thought as well. The problem is that you now need to kind of. If you just add copies, or it should work if you just add copies of obstacles, right? So you just now, instead of having one color on the vertex, you now put 3 different colors, right? So
no, it helps if you parameterize by the total weight, right? But if you still want to remove obstacles with the minimized weight, I'm not sure this will help. Okay, maybe we shouldn't turn it into research seminar, right? But okay, maybe it's good to discuss, I think.
Yeah.
Okay, then thank you very much, Eduard, once again. And
Yeah, thank you for inviting
hope to
me
see
as
you
well.
soon, somewhere, someday.
Yes, it would be nice to meet in person again.
Bye.
Yeah, bye.